Okay, so here's another example of just carrying out a test. So let's go through and walk through. So a software company is trying to decide whether to produce an upgrade of one of its programs. A customer would have to pay $100 for the upgrade. In order for the upgrade to be profitable, the company needs to sell it to more than 20% of their customers. So you contact a random sample of 60 customers and find out that 16 would be willing to pay for the upgrade. So my P hat would be 16 out of 60. Okay, so if I kind of throw 16 out of 60 in, we get 0.267. So that looks like more than 20%. So our question is, that 0.267 is that's basically saying like, hey, that's bigger than 20%. But is that like, it came from a sample, samples aren't perfect, is that far enough bigger than 20% that we could say it didn't happen by chance, okay? So what we're going to do is run this test to decide, could this happen by chance? Could this sample have happened by chance alone, even if it's only 20% of customers are willing to pay for the upgrade? So just a reminder, our first step is choose, where we're going to write our hypotheses. So our null hypothesis and our alternative. My null hypothesis is going to be the 20%, which I'm going to write as a decimal. And we want to know, do we have evidence of more than 20%? So my alternative is going to be P is bigger than 0.2. And P is going to equal the true proportion of customers willing to pay for the upgrade. And in order to test these hypotheses, I would choose a one sample z-test for P. So I've done my choose step. My next step would be my check. Am I allowed to run this test based off of what I know? So my next step would be check my conditions. My first condition is random. And we can say absolutely that we have a random sample. All right, my next condition is normal. And just a reminder, we're going to take our sample, we're still going to do NP and N1 minus P. Now, the way we do this test is we assume this null hypothesis is true. So now we have a value for P to use. So a reminder, when it was an interval, we used P hat here. But because we have a hypothesized value for P that we're using, we're going to use the P from the null hypothesis. Both of those values are greater than or equal to 10, so we are comfortable assuming our P hats are approximately normal. And then my last one, independent. Let's hope that 60 is, in fact, less than 10% of all customers of the software company. Okay. All right, so the next thing we're going to do is do our calculations. And of course, the first calculation is the fact that our P hat is in fact equal to 16 out of 60, which is equal to 0.267. Okay. And as we did yesterday, what we're going to do is we're going to kind of think through, where does our sample fit if that null hypothesis is true? So I'm going to kind of zoom in on this section for a second. Okay, so if the null hypothesis is true, the center of my P hats would be 0.2 from the 20%, right? We're assuming that 20% is true. And the standard deviation of our P hats would be the square root of 0.2 times 0.8 over 60. This is using that standard error formula from our formula sheets, right? And so I can kind of see that my standard error would be the square, just typing this in real quick, 0.051 or 52, okay? And so the first thing we're going to find is what's called our test statistic. It is the z-score of our p hat. So the test statistic is the z-score of our p hat. Well, our p hat was 0.267. Right? And so we're trying to figure out where does that fit. So I'm going to do our p hat minus the null hypothesis divided by that standard error I just calculated. And I did it without clearing out my calculator. If you guys got a slightly different answer, it's fine. So I got 1.297. And then the other thing we're going to do is do our p-value. So when we go to do that p-value, we're going to say, well, all right, if I have a z-statistic, remember z-scores have a mean of 0, a standard deviation of 1. If I have a z-statistic of 1.297, and then the way we decide where to shade is we go back to that alternative hypothesis. Our alternative hypothesis is greater than, so we are going to shade to the right of that value. And then we're going to throw that into the normal CDF. Lower being 1.297, upper being a gajillion, mean 0, standard deviation of 1. And so I found my p-value to be 0.097. Okay, from here, we have to make our decision. So, but before we do that, just like when we were doing confidence intervals and there was a shortcut in the calculator for the confidence intervals, I'm going to show you the shortcut for the tests in the calculator. So let me get my calculator set up for y'all here real quick. Okay, and hopefully it pops up on your screen right now. Okay, and so we're actually going to go into the same menu. If you hit stat, arrow over to tests, and you'll see we have all these options. And before, what we chose was the one prop z interval because we were using one sample and to find an interval about a proportion. When we're doing a test, we're going to choose the one prop z test, which is option 5. All right, and so to take you through that that p0 is the p from our null hypothesis, we're going to put 0.2. The x and the n, so as we go through this, one of the things is if we're going to be using the calculator to do calculator shortcuts to find these values, which I actually highly encourage. Okay, one of the things is the rule of thumb is if you tell it to the calculator, you have to tell it to me. So the first thing we picked was one prop z test. The way you communicate that in your response is when you write down the name of the procedure here. Okay, the next thing we told the calculator was the p from the null hypothesis. That's already been communicated when I wrote down my null hypothesis. So the next thing the calculator wants is x and n, x being your number of successes, n being 60. We've written that in our response when we said p hat, when we said p hat was 16 out of 60, okay? And then the last thing we need to do is say, what is my alternative hypothesis? My alternative hypothesis is a greater than, so I want to pick the greater than the p null. Then you're going to go down, ignore the color, if your calculator even has that, you're going to go ahead and hit calculate. And as you see, when you hit calculate, you can see we have a very, very similar test statistic. a very, very similar p-value, okay? And the reason that the test statistic is a little bit different, the p-value is a little bit different, is because when we calculated here, we used rounded values, and then which made my test statistics slightly different, which made my which made my p-values slightly different. But we're still going to end up coming to a similar conclusion. Okay, so the other component is, so if you have to tell it to the calculator, you have to tell it to me. Also, if the calculator gives it to you, you have to give it to me somewhere. Okay, and as you can see, I wrote all of those pieces of information down. Okay. So next, the last thing we need to do is our conclusion. And as a reminder, when you make your conclusion, the very first thing you need to do is talk about what is informing your decision. And our decision is if our sample is unlikely enough, we reject the null hypothesis and conclude the alternative. So in this particular case, my p-value tells me how likely my sample, where my sample fits relative to what would happen if that null hypothesis is true. So as I'm reading this, the first thing I'm going to do is say, since the probability of my sample, my p-value, and in this case, our cutoff for is this unlikely enough is 5%. Since my p-value is bigger than 5%, my sample's not that crazy. It could easily happen by chance. Okay, so because of that, we don't have enough evidence to reject the null hypothesis. So we are going to fail to reject. Therefore, we do not have enough evidence to conclude that more than, and this is where from here, I'm stealing all the language from this section. Whenever possible. Stealing the language from the question ensures that you are you're communicating with enough detail, okay? Last thing I want to point out, in general, we want our conclusions to be in present tense, okay? So if I said more than 20% of the customers were willing to purchase the upgrade, that were, in the College Board's minds, if you're talking past tense, that words were instead of are would tend to imply that that we're talking about the sample, and our conclusion should be made about the population. The conclusion is saying what our sample says about the population. So we want to make sure we're taking care of that, okay? So hopefully this last example will help. Depending on what time this video concludes recording, please work on either homework or quiz review. We'll have more practice with both. You will have time tomorrow in class to work on both of those things as well. So have a good one. Okay, so as we go through, when we think through the test, I'm going to go back to Joy for a second, because Joy is kind of like our kind of helps us keep track of how and why we make the decisions we make with a test. Okay, and so we all were, by the end, I think, convinced that Joy could smell Parkinson's, because it was pretty unlikely that she could guess right that many times, right? That's what convinced us. Is it still possible that Joy actually cannot smell Parkinson's and she just got very, very lucky? Is it possible? Okay. So as we go through and we do all of this testing and then come to our conclusions, in the end, what's happening is we're still making a decision, and that decision is being made based off of probability, not fact. Okay, like statistics, we're using probability. We don't know for sure. So is it possible we come to the wrong conclusion? Yeah, because we're doing this all from a sample. It's possible that we get like one of those crazy, unlikely samples, and it still happens. Is everybody okay? So In some respects, what we do is we decide, we have to make a decision, is the null hypothesis true, or do we have enough evidence to reject the null hypothesis, right? In the end, our decision is, do we have enough evidence to say it's not true, right? So in any test, we always start out with two possible truths, okay? So the first possible truth is that the null is true. And the alternative is that the null is false. It's one of those two things has to be true. Is everybody comfortable? Do we ever get to know which one? No. But one of them is true and one of them is not. Okay? Now, when we run a test, what we do is we assume that null hypothesis is true. We take our sample and we say, hey, when I take my sample, does that have enough evidence to make me either reject the null hypothesis or conclude the alternative or fail to reject? Is everybody good? Okay. So in reality, when the null is true, we either reject or fail to reject. If the null is false, again, we either reject or fail to reject. Is everybody good so far? Now, if the null is true and I reject it, is that a good thing or a bad thing?
It's wrong.
That's the bad idea, yes? If the null is true and I fail to reject, good or bad? That's good, yeah? What about if the null is false and I reject it? Great, I want to reject bad or false things, yeah? But if the null is false and I fail to reject, that's also a bad decision, yeah? Is everybody good? So it turns out, and so there's kind of two ways we can think about this. You know what I could do? I don't know if you guys know this, but something that you guys know fairly well is already a hypothesis test. We just call it something a little bit different, okay? So let's go ahead and say somebody was accused of a crime. What happens? But when you go on trial for something, we assume you're innocent until we have enough evidence that we don't believe there's another explanation of the crime. Is everybody good? So, your null hypothesis is innocent. Your alternative hypothesis is guilty. Do we see that connection? Enough evidence, we can reject that somebody's innocent and conclude that they are guilty. And let's see, that would mean, so if the innocence is true and I reject your innocence and call you guilty, the mistake is that I'm sending an innocent person to jail. Is everybody good? And if I'm here and I go down this branch, I'm letting an innocent person go free. Everybody good? And here, innocence is false, so guilty, jail. Sending a guilty person to jail is good. That's the correct decision. Letting a guilty person go free would be a bad decision. And so, do we agree that there is a difference between sending an innocent person to jail and letting a guilty person go free? Both of them are a bad mistake, but they're different from each other. Is everybody good? Okay. So, when we run a test, there's two different ways. If we make a mistake, there's two different ways it could happen. Okay? The first one is called a type 1 error. And in order to make a type 1 error, the null hypothesis is true, but we reject it. It would be the equivalent of Joy can't smell Parkinson's and she was just lucky, but we say she can smell Parkinson's. Okay? A type 2 error is that the alternative hypothesis is true, but we fail to conclude it. In other words, Joy can smell Parkinson's, but we say she cannot. We don't say that, or we don't come to the conclusion that she can. Okay? And a way to remember it is if the first hypothesis is true, that's type 1. So both of these are describing I'm screwing up. First hypothesis is true is type 1 plus a screw up. Second hypothesis is true is type 2. To help you remember which one's which. Guys, that's just a numeric choice, okay? So, this will be a good time to pause. Let's take a break. We're going to come back in about 5 minutes, okay? That she's overstating her abilities. Everybody good? Do we see how state what is true and the error being made? Okay? Typically, if you're describing one of these errors in context, the word but should be there somewhere, yeah? Okay. You guys, on this test, at the end, if we conclude she's overstating her abilities, what's a possible consequence? We wrongly accuse her of lying. Man, you lying. But in reality, she's telling the truth. Everybody good? Okay. Type 2 error means the second hypothesis is true. Turner beats Meister less than 70% of the time. But we fail to reach that conclusion. Consequence? She continues to be a little arrogant. I write this example specifically so I can write this sentence because Mrs. Turner is the least arrogant person I know. So it always feels a little tongue-in-cheek. How are we feeling? We feel okay in terms of okay. Now, in this setting, do you think one of these mistakes, and really the consequences help us make this determination, is one of these mistakes more serious than the other? Do you have a mistake you'd rather make? Yeah, which one is it? You'd much rather, in this case, specifically you guys, I would think, would much rather let her stay a little arrogant than wrongly accuse a teacher of lying. Me, I might be like, yeah, I could be wrong and you're lying. Or I wouldn't want her to stay arrogant. But that's just silly. Everybody good? Okay. So, describing each error based off of the hypotheses. So, one of the things that you guys will find is I might give you, say, a free response question that asks you to describe a type 1 or a type 2 error. If I don't ask you to write the hypotheses, you don't have to. But I don't know how you come up with your type 1 and type 2 error without having hypotheses written down. I don't answer those questions without writing down my hypotheses first. Okay? Okay, great. And you guys have decided that type 1 is more serious because for sure. Okay. Now, we were talking the other day that sometimes we use alpha equals 1%. Sometimes we use alpha equals 5%. Sometimes we use alpha equals 10% and everywhere in between, okay? So the question becomes, why do we use these different values for alpha? Okay. So what we're going to do is we're going to, I'm just rewriting these from the previous page. Let's go ahead and assume that null hypothesis is true, okay? And we're going to say we take a sample of size of 100. And what do we know about the possible p-hats if my null hypothesis is true? Well, we know the center of those p-hats is 0.75. We can figure out the standard deviation of those p-hats. Thank you. All right, and in some respects, let's see. So if I got let's just say we go take a random sample right now, and we get p hat equals 0.73, so right about here. Are we going to reject our null hypothesis here? What about if I got 0.7? Probably not. 0.68, maybe. 0.4, definitely, right? Is everybody with me? Okay. And so, for right now, let's let alpha equal that 0.05. And let's go ahead and say that this area right here is 0.05. Okay? So, what can we say if my p-hat's right here? My p-value would be the area to the left of this, yeah? Because it's a less than hypothesis. So if I'm right here, I'm shading left. Are you with me that if my p-hat's right here, my p-value will be less than 5%? Or more than 5%? And here, more than 5%. Here, less than 5%. You guys with me? So it's almost like everything in this section, everything in this section I would fail to reject. And everything in this section I would reject. And sometimes old school statistics teachers would even say that this is what we call the rejection region. And in fact, because we know this information, we could even figure out, so it's like there's a cutoff value that tells us when we're going to reject and when we're not going to reject. Is everybody good? And if I asked you to find what is this cutoff value, could we do it? Using inverse norm in our calculator, right? Can you guys help me out with using that inverse norm? What is that area? Please and thank you. I'm sorry? Well, the area is, I'm sorry. What is the boundary? What is the boundary when my area is 0.05? Would this mean this standard deviation? Because if I ask you for the z-score of where, yes. 0.6792, great. Everybody good? That seems about right to me. That feels pretty good. Okay, hold on. Now, have we taken a sample yet? Okay, do we know what is true? The null or the alternative hypothesis. Do we know which one is true? We created this assuming the null is true. Okay? No, but no matter what happens to be true, this set of hypotheses with this sample size we're going to reject our null hypothesis if we get a p hat that is less than or equal to 0.6792. Again, we haven't taken a sample, we haven't run a test. This test, because of the way it is structured with a sample size of 100, with these hypotheses, will reject the null hypothesis whenever we get a p hat that is less than this value, because it'll be somewhere in this tail. We feeling okay? You will never have to do this. Okay? But it's laying the groundwork for a concept that is a big idea. Okay? All right, hold on. What did we assume on this graph? That the null hypothesis is true, yeah? So, can we talk about errors? If the null hypothesis is true, if I make an error, it is a type 1 error, yes? And I make a type 1 error when I reject the null hypothesis, even though it is true. Is everybody good? So, if I were to ask you in the picture, where on this picture is the type 1 error? It's right here. That's where I'm going to reject when the null hypothesis is true. Right here, fail to reject, that is good decision. Is everybody good? Okay. So this is a correct decision. This is a type 1 error. So, what is the probability of a type 1 error, according to this picture? 5%. So, alpha is your probability of making a type 1 error. If I chose, instead of alpha equals 0.05, I said, hey, I'm going to do alpha equals 0.01. What I just did was lower the probability that I make a type 1 error. How are we feeling with that concept? Okay? So in the how come sometimes we use alpha equals 0.01 versus sometimes we use alpha equals 0.05? Okay? The reason we do that is because alpha is the probability of type 1 error. If my type 1 error is really serious, I might want to use a pretty low alpha to decrease the probability I make the more serious error. Everybody feel good? All right. Something else I want to point out that kind of relates to this, okay? When we talked about experimental design, we said every experiment needs to have control for potential confounding variables. We needed to have random assignment. And then we had to have something called replication. You guys remember? And replication was really hard to understand. Okay? But what replication means is if somebody else ran the exact same study with the same design, they get similar results. So, as you read studies, scientific studies, whatever, you'll sometimes hear like, oh, we have significant evidence of this, and then later on you'll hear about a study was debunked because further studies couldn't replicate it, okay? It is very, very possible. In fact, if we use alpha equals 5%, 1 in 20 studies is going to come up with a significant result, even though it's not significant. Because 1 in 20, 5%. 5% of the time, this could be true, and I'm still grabbing one of these samples 5% of the time. We never get to know. But so that's one of the reasons when we talk about replication means we have to get that same result a couple of times to make sure it's not just this by random chance we got one that was in that range. Are we good? Okay. Now, Yeah, well, that was a poorly written sentence. All right. So, you guys, I don't think this should say 79% of the time. Let's go ahead and change that because it doesn't really make sense. Let's say she really only defeats me. You know, I'm going to say 62% of the time. So let's say her actual winning percentage is 62%. What would the p-hats look like then? They'd still probably be normal. What would their center be? It's 0.62. The standard deviation is going to be pretty darn close. It's going to be a little bit different. $100.
0.0485.
Could this be true? Could the 62% be true? We don't know. Could be 68%. Could be 73%. We don't know, right? Hold on. If this is true, what can we say about our two hypotheses?
HA is true.
The alternative is true. We should reject the null, yeah? We should reject the null. Okay. When are we going to reject the null? I'm going to reject the null whenever my p-hat is smaller than this, regardless of what is actually true. Yeah? Okay, hold on. So if I draw that picture in, here's that 0.6792. I can shade this way, right? This equals reject. This little tail here would be fail to reject. Hold on. Which one? So, hold on. Good decision, bad decision.
Good decision.
This is a good decision. I want to reject and conclude the alternative if the alternative is what is true. Yeah? So, here, if this graph is what is true, this is a good decision. And this tail here is a type 2 error. Hold on. Now, let's kind of zoom out here. Which graph is true? I don't know. Could be neither. Right? It could be that the actual proportion is 63.752%. We don't know. We'll never know the actual proportion. That's what makes this whole concept really murky, okay? And so what I want you guys to focus on is the decision, okay? And what's influencing our decision. Now, let's say instead of using alpha equals 0.05, I use alpha equals 0.1. What happens here? My cutoff point's going to move closer, right? Because 10% is bigger. What's that going to do to this graph? It's can make this section smaller. Is everybody good? So I increase my probability of a type 1, and conversely that decreases my probability of a type 2. Is everybody okay? All right, so could we find on this graph what is the probability we make the correct decision? We would just say, well, what is the probability we get that p hat that is smaller than 0.6792? Yeah. I typed it in wrong. All right. That probability is called the power of the test. In specific, it is the power to detect p equals 0.62. All right. So, power plus the probability of a type 2 error. Okay. You guys. Power is the alternative is true when we make the right decision. A type 2 error is the alternative is true when we make the wrong decision. So what should these two things add up to? They should be 1. Because they're complementary events. Both of them are the alternative is true, good decision, bad decision. Everybody okay? And they exist separately from alpha because they're on a different graph. Okay? They're under what I would call a different truth. Okay? But they are related. However I move alpha is how I move the power. Okay? Power goes with rejection. Alpha is the probability I reject when the null hypothesis is true. This is the probability of a type 1. So power and alpha both go with rejection. Power is HA is true. Alpha is HO is true. We're starting to kind of see how this goes. Okay, a couple other things. So our picture kind of looks like that. Every good? All right. All right. Everybody okay? Again, these two only occur if the alternative is true. This is calculated as if the null is true. And we actually do all of our calculations if the null is true. Okay? All right, so power is a good thing. Power means the alternative is true, we're making the correct decision. There are several ways we can increase the power. We increase the probability in general of making the correct decision if we have a larger sample size. If we increase alpha, we increase power. And the way you can remember that, increasing alpha increases the probability that you're going to reject the null hypothesis. There's more samples whose values will give you a probability less than 10% than less than 5%. Okay? That area that we covered, this area, gets bigger. Okay? Just sneeze. Maybe not. Okay? Lastly, power is always calculated. You'd be given some sort of alternative. So if I had drawn this picture, and what if instead I had put 68% here? Is everybody with me? My power would be smaller. If I look at that picture of 68%, in fact, my power would be less than half. Because I'd be rejecting, remember, we're still only rejecting less than 0.6792. You guys seeing it? Okay. As you're going through, the way I've seen this asked is like multiple choice questions of which would have the most power. Whatever makes you most likely to reject the null hypothesis is the most power. Because power only happens when you reject the null hypothesis. Okay? All right. Okay. Oh, hilarious. That tree diagram that I drew on the previous page, I was like, it should go here. Okay. All right. So lastly, if type 1 is more serious, you want lower alpha. Lower alpha means I'm less likely to make a type 1 error. I am more likely to make a type 2 error. Right? Type 1 error happens when I reject, and I shouldn't. Type 2 error happens when I don't reject and I should. So they can't work in the same direction. If I'm increasing my probability of type 1, I'm decreasing type 2 and vice versa. Okay? If a type 2 error is more serious, we might use a higher alpha. I've never seen alpha bigger than 10 or 15%. Okay? Alpha is definitely the probability of an error. Power is a little ambiguous because you don't know what the alternative being true actually means, right? It could be 0.62 or 0.68 or 0.73 for that previous example, okay? So power is pretty ambiguous depending on the alternative hypothesis being true, okay? How extreme that is, okay? So we typically don't let alpha get much bigger than 10% because we don't want more than a 10% likelihood that we screw up. It's just how we screw up. Okay? Everybody good? I am not going to do confidence intervals for proportions today. That's going to be way too much for you guys. I will give you guys, I'm going to give you guys a day to process what was just said, because this is a lot. This is as into the weeds of abstract thinking about stats that you guys are going to have all year. Okay? This is by far the most abstract, weirdest thing. Okay? Tomorrow I'm going to show you a different kind of visual to help you visualize what's going on with all of those different components working together.